All right, so we've talked so far when we're trying to figure out congruence and divergence. We've talked about looking at the geometric series. We've talked about the test for divergence. We've talked about the integral test. And we've talked about the p-series. So tonight we're going to add the comparison test, the limit comparison test, and the alternating series test. Sounds like, wait, you just said the class was going to be easy and I'm adding 3 new tests. These tests are actually pretty simple, and they rely on other stuff that we already know. So it won't be, it's not as bad as it sounds. So let's look at this series over here. So we have this 1 over 2n plus 1. Looks really simple. Kind of looks like a series that I would know. But because I have that plus 1 in there, it's just not a simple geometric series. However, we can start to look at things. I know that 1 over 2n plus 1 is going to be less than 1 over 2n. Because my denominator is getting a little bigger, which means this one's going to be a little smaller than this one's going to be. So I know this one's always less than this one. Now this series, the 1 over 2n, (1 over 2 to the n power), that is a geometric series, which we can rewrite as 1/2 times 1/2 to the n power, n minus 1 power. So now it's a geometric series. Since it's geometric, I can determine if it's going to converge or diverge. Now this one, we know is going to converge because my r equals 1, or 1/2, sorry, which is less than 1. And if you remember, it converges, since I know it's a geometric series and it converges, it's a over 1 minus r. So it's 1/2 over 1 minus 1/2, which equals 1. So that's how they got that. So I know that this side right here is going to converge to 1. And since I know this is less than that, I know this part has to be less than 1. Does that part make sense? Not the reason why I'm doing it, but does what I did make sense? It logically doesn't make sense, I should say. All right. I would hope you'd say yes if you, or no if you don't really get it. So now, when we're looking at this one right here, one of the things that we talked about at the end of class last time was bounded series and monotonic series. And remember I said that if it's bounded and it's monotonic, it's going to always converge, because it's going to a specific value and it's not going to go outside of this value. So this series right here, I know is going in one direction. So as I'm adding this, this is going up. But I also know that it's never going to go above 1. So since this is basically monotonic and I know it's bounded by this, I also know that this series converges. even though we technically did nothing with this series. We know it converges because the other thing that I'm doing, the other thing that I'm comparing it to converges, and this always has got to be less than that. And that's the basis of the comparison test. The comparison test is two different ways to look at it. It says if the new thing I'm looking at, or if B to the n is convergent. So this is the thing I'm comparing it to. And the thing that I want is always less than that. Then the A to the n is also convergent. The other way is if Bn is divergent, and what I'm looking for is always greater than that, then the AN is also divergent. The two things we want to compare things to are ones that I can easily find the answer to. The geometric series and the P series. Because those are two that I can easily determine if they're going to be convergent or divergent. So P series and geometric series are going to be our friends when we do the comparison test. All right. Actually use it. So first we're going to look at is this one. We want to determine if this one converges or diverges. So what we need to do when we're looking at comparison is we want to find something that is similar to it. When I'm doing that, what I typically will look at is I will look at the numerator and the denominator and eliminate everything except for what is the most important parts as it gets extremely large. Because remember, we're basically looking at the limit as it goes to infinity. So when we're looking at things that go extremely large, what's the thing that's going to take over that function? So in this problem, my numerator is just 5. So I'm going to keep my numerator as just 5. The denominator, as I'm getting bigger and bigger, the 3 will get dropped off first, because if n is 1,000, I've got 4,000 right there, and I've got 2 million right here. The 3 doesn't matter much at that point. And actually, even if I do that, I've got 2 million right here. 4,000 is not that big of a deal. So just by even going to 1,000, the only thing that really matters that's going to impact it is that first part there. So I'm going to compare it to 2n squared. Does that part make sense on why I was able to eliminate the other stuff? Because that's probably the most important part of this process, is looking at what we're going to compare it to. So, go ahead, Scott.
No, I was just gonna say it makes sense.
Okay. So there's a couple things we got to look at now. The first thing is this function less than or bigger than the other function? So in this case, we've got 5, 2n squared plus 4n plus 3. That's always going to be less than the 5 of the 2n squared, because these things are added to it. So that means that part right there is always going to be bigger. The denominator is going to be bigger here, so therefore that function is going to be less. So that's step one. I need to make sure that my new function, my Bn, is, or my An is less than my Bn, or my Bn is greater than my An, depending on how you want to read it. All right, so that's the first thing. Second thing we need to do is we have to figure out, does it converge or diverge? So by 5/2n squared, this kind of looks like a geometric series, the way that it's set up. So I can pull out the 5/2, and I'm left with the 1/n squared. So actually, this isn't a geometric series. This actually ends up being a p series. So because my exponent is numeric in this case. So this is a p series. And my p-value is 2, which is greater than 1. So it converges. So remember, p-series and geometric series are going to be our friends when we're looking at these. And the geometric series is when the variable is in the exponent, and the p-series is when I have a numerical exponent.
And
All right.
the p-series is just numerical exponent. That's it, right?
Yep, just a numerical exponent. And as long as it's greater than 1, it's going to converge. So
As long as the exponent is greater than 1.
correct.
And it doesn't matter whether or not that's that the exponent, excuse me, that the variable is in the numerator or denominator, as long as it's greater than 1.
No, the p-series has got to be in the denominator.
Got it.
Because if it's in the numerator, it's going to go to infinity no matter what.
Got it.
It's got to be the denominator. So basically, it's 1/n to the p power. All right, so we know it converges, and I know it's less than. So therefore, since it converges, and this is true, my original series, my an, also converges. And that's by the comparison test. So basically, we're looking at those two pieces. This has got to be true, and it's got to converge for it to be convergent. Okay. Let's look at this one next. This one we've actually already done. We did the integral test for this one on class on Thursday. And we found out that it diverged. So let's look at this actually as a comparison test now to see if we can, instead of having to do the integral test, we can do it as a comparison test. This one's got the ln of k in there over k. So there's nothing really to change in the denominator. So I'm going to leave the denominator just as k. However, I have an ln in the numerator. And I know, so this is where the comparison test really has that little bit of a sense, like you have to logically start thinking about things. It's like, we want to find things that we can compare it to, and we want to pick things that we know either they converge or diverge. So, but they have to have some relationship back to the problem. So in this problem, I'm actually going to say, I'm going to make this 1/k. Because I know that the ln of k is always going to be greater than 1. All right, because no matter what number I plug in for k, ln of k, that number is going to be bigger than 1. Does that make sense?
And that's just because because E is such a small number. Is that what you're saying?
Well, no, because so even forget the e and everything else. Like if I was going to solve it, if I plugged in ln of 0, or actually rephrase this, ln of 1 is going to be 0. So any number that I plug in for k after the e basically is going to be greater than 1. So as that number, because remember, we're looking at it as it gets larger and larger, right? So as ln of k gets larger and larger, I know all those numbers are going to be bigger than 1. It's never going to be smaller than 1. So I don't really have to worry about that one little case at the very beginning where it's a little less than 1. That's where we did the integral test where we said once we hit e, it's going to continue to, well, in that case, increase. It wouldn't actually change going up and down. So same thing here. It's like I know ln of k is always going to be greater than 1. So I can use it. Same reason we did in the last one where we looked at the denominator. It says I can just ignore the 4n and the 3 because they really don't matter as I get infinitely large. Those are kind of just going to get washed away. Does that make sense?
Yeah.
So now that I know that I have this comparison, this right here, the 1 over k is what? What's the special name for that?
Derivative of ln.
Nope. Well, yes, it would be the derivative of ln, but not in terms of a series. There's a specific name for that 1 over anything. 1 over k, 1 over n, 1 over x, depending on how you want to write it. There's a specific name for it. Do you remember? There's actually one of the series I told you is very important, and you're going to need to know its name. It's the harmonic series. Because it's the one series that it looks like it's going to converge. But remember, we went through and did it, and 1 over k actually diverges. So we know the harmonic series always diverges. So the comparison test states that if an is bigger than bn, and this diverges, this also diverges. So these theories of k equals 1 to infinity of ln of k over k diverge.
Now, this might be a kind of basic question, but I know these are no longer sequences, they're series. So they're all adding up to something, right?
Correct. Yep.
So the an value there, that's all of the values up of the sequence added up to the nth degree.
No. So the an and the bn actually is just looking at that series as it's going to infinity. So yeah, actually, yes, it is the series. Sorry, you actually said it right. I'm sitting there saying it in my head, and then I'm like, nope, that was the way I said that was wrong. Yeah, it is the series as that. So it's not. I'm not writing it because I just don't feel like writing them all, like summation symbol, which is annoying to write a million times. But yeah, that's the series of a to the n, or series of an.
And series means all of the values up to that point added together, correct?
Correct. Yep. Because like 1 over k, if you just look at that as a sequence, that's going to 0.
Mm-hmm.
But when you add them up, it actually ends up diverging. It doesn't go to 0 fast enough to converge.
Got it. Okay.
That's that's that weird one. That's why the p, because in essence, that's a p series. That's p to the 1, first power. So, and that's why it doesn't converge. It doesn't converge at p to 1. It converges when p is greater than 1.
Oh, right, because the exponent is exactly 1 and it is not
Correct,
greater than 1.
correct. Yeah, it's not greater than or equal to, it's just greater than. So, and that was why, is because the harmonic series actually diverges and doesn't converge at that point. That's also the reason why we can't use the test for divergence. The reverse of it's not also true. But it says for divergence says if it comes out to be 0, or if it comes out to be anything other than 0, it diverges. But we can't go, well, if it equals 0, then it converges. And it's really the harmonic series that is the main one that we see that shows that that isn't true.
And when it says, when we're saying they eventually, as a series, all values eventually diverge to a value of infinity, is that the correct language?
Yeah, it basically goes to, it just, yeah, basically it's going to go to off to infinity, or you can either say it goes to infinity or the summation does not exist because it doesn't go to a real number. So anytime it diverges, you're not going to come up with a value. If it converges, you can come up with a value. It's a matter of how much work you want to do to figure out exactly what it is.
Thank you.
No problem. All right, let's look at this one. What makes this one different than this one? What makes these two problems different?
The plus one or minus one on the bottom.
So this problem right here, we originally said we know that that's always going to be less than 1/2 to the n, right? And we did that because as we get bigger and bigger, the 1 basically vanishes. So the question is, if we did the same concept, this would also be 1/2 to the n, right? However, is it this way? Is it less than or greater than? That's the question. So if I'm subtracting 1, is this one going to be less than that or greater than that?
Should be greater than.
Going to be greater than. That is correct. So this right here, we know converges. However, for it to converge, AN has to be less than BN. So based on our comparison test, I can't use the comparison test for this function because it converges and it's the wrong direction. Basically, since I know this converges, so this is going to go to a number, but this is bigger than it. So I don't know if that number is also going to go to or converge because it's bigger than it. It might be slightly bigger, but it's still bigger. So I'm not sure what's going on with it. So we
does the
can't.
comparison,
Huh?
so does the comparison test only apply for divergence?
No, the comparison test does for both. However, they have to be a specific direction. So if we look at the comparison test, there's a very specific order that matters. If AN is less than BN, it's convergent if the BN is convergent. So if what I'm comparing it to is convergent, it has to be less than that. If what I'm comparing is divergent, it has to be greater than it. So if these symbols are the wrong direction, like the one I just looked at, it said BN is convergent, but AN is greater than BN. I can't do that function or that test for it. That's why when we did it, we looked at both pieces. We said we had to figure out if BN was convergent or divergent, and then we had to look at the direction of the comparison. And then we were able to say if it was convergent or divergent. So in this one, my BN is convergent and my AN is less than my BN. So therefore, AN is also convergent.
Got it.
And this one we looked at, we said BN is divergent and AN is greater than BN. So therefore, they both diverge. In this one, we said it's convergence. However, AN is bigger than BN. So that fails that part of that test. So we can't use the comparison test. So we have what's known as the limit comparison test. So what the limit comparison test does is we're going to take both those. We're going to take the AN and the BN, as long as they are both series with positive terms, so they can't go negative. So we're still only dealing with positive terms, and we looked at that even in the other problems. They had to be positive terms to deal with it. As long as the limit of that goes to a specific number. Doesn't matter what that specific number is, as long as it's greater than 0, which makes sense because they're both positive. It has to go to a specific number, not to infinity. Then either both series converge or both series diverge. So this is for those situations where it goes the wrong direction for the comparison test. This allows me to test it a little differently. And then the direction of it doesn't actually matter because we're going to do comparison with this test. So let's do it with the one we were just looking at. So I'm going to make my AN the 1 over 2n minus 1. And my BN is 1 over 2n. So now my limit is the division of these. So it's the limit as n goes to infinity of 1 over 2n minus 1, and then 1 over 2n. Remember that division of fractions, you just keep the first one for the second one. So I have 1 over 2n minus 1 times 2n. What? So I get 2 to the n over 2 to the n minus 1. Now, what was the little shortcut that we used to simplify these things down? When we divided them all by the highest exponent, which in this case is n. So we're going to divide the entire problem by 2n, 2 to the n. So I've got 1 over 1 minus 1 over 2 to the n. So that goes to 1. All right, and for this rule, it was just that number had to be greater than 0 and go to a specific number. So it goes to a specific number, and 1 is definitely greater than 0. So since Bn converges, An converges. And that's using the limit comparison test.
Wait, say that last part again. I don't understand. 1 is greater than 0 after that.
So the rule for the limit comparison test said that whatever this value is, C, has to be greater than 0 and be a finite number. So actually a number. So in this case, my limit came out to be 1. So that's C. C is greater than 0 because 1 is greater than 0. So that's the only criteria for the limit comparison test, is that when we do this, C has to be a finite number and C has to be greater than 0. If that's true, then whatever the Bn series does, the An series has to do. So since, in this case, Bn converges, An converges.
So I'm assuming there's going to be cases where it's not greater than 0, right?
It could be 0, or it could go, or this limit could go to infinity. So that, yes, those can happen. In which case, if that happens, it doesn't give you any information. So if you notice, it does not say if this is not true, then it does the opposite. So
Right.
if, just like the other test that we did, if the test fails, it doesn't give me information. So just like this test failed. This was a comparison test we did and it failed. It didn't tell me any other information other than it didn't work. So then I did the limit test on it. That test succeeded and gave me my information.
The two situations where it would fail is if the series goes to infinity or is less than 0, right?
Yeah. The chances of it being less than 0 is slim, actually. It might equal 0. Just because, remember, both these things have to be positive. So if they're both positive series, taking a limit going to a negative number is probably not going to happen.
Okay.
But it could definitely equal 0. That actually is a possibility. So. This. Trying to find a limit comparison test that it doesn't work in their examples. My odds are they're not going to give me an example that does that. But they don't. All right, let's look at this one. So the comparison tests work really well when you can simply compare things. Like figuring out if the numerator stays the same or the denominator stays the same, that's going to kind of help you. The problem that happens when you're trying to do a comparison test where they both change, it becomes really hard for you to determine if one's going to be greater than the other one or one's going to be less than it. So whenever you get something a little more crazy where things on the top and bottom change, you're probably not going to just be able to do a simple comparison test. You're going to have to probably look at the limit comparison test. which is what we're gonna have to do in this one because my numerator and my denominator both change. However, we're gonna do the same thing to determine what happens as we get infinitely large to find that comparison piece. So in this problem, my an is 2n squared plus 3n over the square root of 5 plus 10 to the 5th. My bn in the numerator, my 2n squared is going to stay because that's the biggest part of it. And in my denominator, it's going to be n to the 5 halves. Or if you want to write it, that's just the square root of n to the 5th. Because that part's going to take way over that 5. That 5 is not going to mean much. So, which I can now simplify to 2 over n to the 1 half. Does everybody see how I'm simplifying down to find my comparison term? All right. Now, there's no real easy way for me to determine if an is greater than bn or an is less than bn, because things both change. So when we're looking at this, we're going to have to do the limit comparison test for it. All right, so before we do the limit comparison test, let's figure out what this is. This right here is a p-series with p equal to 1/2, which is less than 1, so it diverges.
Wait, Professor, sorry to backtrack a little bit. I'm trying to figure out the exponent thing here. So it's 2n squared times n to the negative 5 over 2. And then when we multiply them, right, we're supposed to add them.
Yep.
So, oh, until n 1/2. Okay, thank you. Sorry.
It's okay. All right, so now we've got our, we know this diverges. Now we've got to do our limit comparison to see what it comes out to be. So it's going to be infinity. If you want to write this as two separate problems immediately instead of having to try to put them together, you can do that. So it's an, remember it's an over bn. So the an part stays. As is, and the bn side switches or flips. So that's n to the 1/2 on top and 2 on the bottom. So I've got 2n to the 5 halves plus 3n to the 3 halves over 2 square root of 5 plus n to the 5th. My highest exponent in this case is Heilige. Okay, go ahead. All right, so my highest exponent in this case is 5 over 2. So I'm going to divide everything by n over 5 over 2. So I get that just becomes 2 plus 3 over n on the top. And the bottom becomes 2, 5 over n to the 5th plus 1. And that limit then becomes 2 over 2, which equals 1. They don't always come out to be 1.
Could you explain how you divided the denominator by 5/2, by n to the 5/2?
Yeah. Let me just rewrite it real quick. All right, so this right here, the top becomes the 5 plus n to the 5th. The bottom is just the square root of n to the 5th, which then puts, you can put it all under the same thing. So, which ends up giving you the square root of 5 over n to the 5th plus 1.
Thank you.
Welcome. So 1 is greater than 0. So since my original function diverges, that means an diverge, which is my original series. So
So the reason why it's 2/2 is it because as the n gets larger, that 5/n to the 5 just becomes 0, and then 0 plus 1, square root of 1 is just 1, so just 2/2, right?
correct. Yep. That's why we do that division step, because in essence, what it does is it takes everything and puts it in the denominator. So, and as we're looking at the limit, as the denominator is getting increasingly large, that goes to 0. So that basically eliminates those values that are going to go to 0. So in this case, I'm left with the 2 on the top, and then the square root of 1 is just 1. So that's how I'm left with the 2 on the bottom. All right. Next test.
Is that like the hardest one we've done so far?
What, the hardest test or the hardest problem?
Hardest problem.
Probably. I don't think that's, honestly, the integration tests ones were probably a little harder. But we probably did some simpler integrals. So that's the thing. It's like the problems, the comparison test really takes problems that look really complex and gives us a way to simplify them down so we can look at something simpler. And that's why I was saying that P series and the geometric series are going to be your two best friends. Because if I can get it to a P series or I can get it to a geometric series, I'm done. I can tell you almost instantaneously if they converge or diverge. And the comparison test piggybacks off that. Because as long as I can take a problem and simplify it down to one of those, now I have a way to compare it and figure out if it's going to converge or diverge. So we can take really complex problems like this and simplify it down basically to next to nothing to do. So otherwise, we would have had to do like an integral on this one, which would have been a nightmare. All right. Next test, the alternating series test. So first thing we have to figure out is, what is an alternating series? An alternating series can be one of two situations. Actually, an alternating system is always going to be, it's going to alternate between positive and negatives. It doesn't matter what it starts off with. It can either start off with as positive and then go negative, or go negative and then positive. Notice that when we're looking at these, this piece right there will dictate and tell you which direction it's going to go. If it was n-1 or n+1, it's going to start off as a positive. If it's just n, it's going to start off as a negative. So that right there tells you which one's the first one's going to be. That's the key to alternating. Everything else after it actually does not matter in terms of determining if it's an alternating series. It's just that -1 raised to an n power. Now, the key is, once I know they are an alternating series, we have a test that we can do. And this test is going to tell me if it's convergent or, well, actually just convergent. This is the alternating series test. So the alternating series test, you have to start off with an alternating series, and it has to satisfy two cases. The first case is that every term is decreased from the one previous. And so if you look at this, notice that that's Bn. That's the Bn. It's the thing that's after the alternating piece. So we're going to ignore the -1 as long as my terms are getting smaller as they go. That satisfies criteria number 1. Criteria number 2 is the limit has to equal 0. So the limit of that sequence of just Bn has to equal 0. If both those are true, the series is convergent.
And this only for those that start even?
No, it could start any way it wants.
Or, I
It
mean,
just has
positive?
to, it has to go positive, negative, or negative, positive. It doesn't matter which direction. It just has to alternate.
But it says there that all has to be greater than 0, right? The first condition there.
No, the first condition states that so if we look at this piece here, this is the important part. So if we look here, notice the Bn is not the alternating part. So An is the -1, n-1, Bn. This is the piece I'm looking at right there. When we're looking at those two cases, we can ignore the alternating piece when we're looking at those two cases. The only thing the alternating piece is important for is to tell me I can use this test. Does that make sense or no? So Bn is always going to be positive in this situation. So if we just look at Bn for this first one, it's going to be 1, 1/2, 1/3, 1/4, 1/5, 1/6, so on and so forth. Not positive and negative. Because the Bn in this case is not the series, I mean, is just the sequence, not the actual summation series. We're just looking at that sequence of 1 over n, or in this case, n over n+1.
But in the next page, it specifies that it be positive and negative, right? Because it says negative to the n-1.
They just use that. This isn't, this is the alternating series. This doesn't matter. It could be just n there. It doesn't make a difference which order it goes. So because even though they didn't write this second one, it still counts. So
when they're saying Bn has to be greater than 0, they're saying as long as the sum of all of those is greater than 0, that's the first condition, right?
what do you mean? The first condition just says that the sequence is going down, is decreasing basically.
No, I know, but it says there at the top right, it says Bn greater than 0.
Yeah. Oh, okay. I see what you're saying. Yes, because it's got to be that sequence is going to be a positive sequence because I'm taking out the -1. Let's do one. I think that's going to help you see what I'm talking about. And I'm not going to do that one first. I'm going to do this one first. All right. So here's my series that I'm going to compare. Step 1. Is it an alternating series? Yes. So it's alternating because it's got the -1 to the end. So it satisfies the alternating series test. You agree with that one? You understand where that came from?
Right.
Okay. So Bn is 3n over 4n minus 1. So that's Bn. That is greater than 0. Okay.
Yeah, I guess. Wait, how can we make that statement?
Is that so? Remember, n starts off at 1. It's a series, so n has to equal 1. Goes up from 1. So if n is 1 and goes up by, so it's 1, 2, 3, 4, 5, all the way up. Can that ever be negative? True. That's the main thing. That's why I said when they're saying Bn, that part right there, that Bn is greater than 0, you're never going to fail that condition. Because this problem, this Bn is never going to have a negative sign in it because we've removed that from the alternating piece. And n can never be less than 1 because of the concept of how the series works. So since I'm starting off at that, that can never be, and they're always whole numbers because we're counting going up. That's the way the series works. So since I'm never going to have a fraction, I can never make that a negative number. So that's that piece you never really have to look at. The main piece is it alternating and does it satisfy the other two conditions? The other two conditions were, so condition 1 is Bn plus 1 is less than or equal to Bn. And condition 2, the limit as n goes to infinity of Bn equals 0. So those are the two conditions. It doesn't matter which one you test first. Makes no actual difference. I look at the problem and then I determine which one I want to test first. So in this problem, my numerator and my denominator both change. So telling me which one's going to be less and greater might be a little difficult to do off the top of just quickly. The limit one might be faster to do in this case. So we're going to look at the limit in this case. The reason why you want to pick which one you start with first is if it doesn't work, you're done. You can go, you don't have to go any further. So that's why it's a nice thing to choose which one we want to do first. So in this case, I'm going to do condition 2 first. So I'm going to look at the limit as n goes to infinity of 3n over 4n minus 1. So to do this one, I'm going to divide them all by n. So I get 3 over 4 minus 1 over n, which equals 3/4. So that does not equal 0. So it fails the alternating test. And since it failed the alternating test there, I don't need to look at the first one. Because it doesn't matter, it's got to pass both tests to work. That makes sense?
Could you go back to the slide with the rule real quick, Professor?
This
So we're testing specifically for convergence, not this. This will tell us nothing about divergence.
kind of. But yes, the alternating series test does not tell me divergence. It only will tell me if it converges or not. However, there's a caveat to that, which I was about to tell you. All right. Look at these two rules. So the alternating series test, I have this rule right there. So if it's converged, if that has true, and the other ones are true, then it's convergent. Those two rules right there are basically the same rule. So if it fails criteria 2, that limit does not equal 0, then by the test for divergence, it passes the test for divergence and it is divergent. So this series fails the alternating series test. However, it passes the divergence test.
Is there a scenario where it would fail the convergence test, excuse me, the alternating series test, and not pass the divergence test?
Yes. If it fails, if it passes criteria 2, so it's just through criteria 2. So if it fails criteria 1 but passes criteria 2, it still wouldn't be convergent. However, it also would, your test for divergence wouldn't work because it does equal 0.
Say that again, please.
So so in this situation, what we just did, it failed criteria 2. That's why we were able to go to the test for divergence. If it failed criteria 1, but passed criteria 2, then it wouldn't tell me anything about divergence. Does that make sense?
Got it.
So that's the piece. So yes, it could fail and not do the test for divergence. That's also one of the one of the reasons why you try criteria 2 first, because if that one is one that you're going to have to do for other tests to begin with, so it's nice to do that one first.
So let me just reiterate that. So if it passes criteria 1,
Yep.
but fails criteria 2,
Then it would be divergent.
right?
If it fails criteria 2 anyway, if it fails it because it doesn't equal 0, it's divergence because it passes the test for divergence. The only situation where the test for divergence would not work is if it failed criteria 1 and passed criteria 2. And off the top of my head, I can't come up with one that would work that way right now. So And every example they give me, if it fails the alternating series test, it passes the test for divergence. So. But I know for a fact that that doesn't always work. I just can't come up with an example that would happen right now. All right. Look at this one. All right, so we've got this one. So I've got my Bn is n squared over n to the third plus 1. So let's look at my limit. N squared over n to the third plus 1. So I'm going to divide everything by n to the third. So I've got 1 over n. And I've got 1 plus 1 over n to the third. So it's 0 over 1, which is 0.
Are we gonna talk about the fact that that n plus 1 is not in the form of either alternating series? Do we worry about that?
No, because it's still going to alternate. Because the first one would be positive. Because it's -1 to the 0 power, or -1 to the second power, which is positive. And the next one's going to be negative. So the only time, actually, I'm trying to think of where it wouldn't actually always alternate. If it was like 2n plus 1, technically it'd always be odd. So it would always be negative. And if it was just 2n, then it would always be even, it would always be positive. So yeah, focus less on that n minus 1 or n plus 1 or n. As long as the series, like when you look at it, is going to go back and forth between the negative and the positive, that's all that really truly matters. The reason why that's there is because that's what gives you the alternating thing. And the only other situation where you could possibly get ones would, like, think if you're like looking at sine or cosine. Sine and cosine do alternate, but they don't alternate every other term. So they do go from negative to positive and back and forth, but it's not every term. So therefore, that wouldn't be an alternating series. An alternating series, every term has to switch the sign. And that's where that -1, n plus 1 still does that, even though it's not an n minus 1 or an n. That make sense?
Got it.
That's why I said, like, when we're looking at these, as long as you can tell me it's alternating, you don't even have to look at that as an actual test. We know this is alternating because of that piece, move on. And notice I tested criteria 2 first again. I like testing criteria 2 first because it doesn't make a difference which one you do first. And that one's the easy one. It passed criteria 2. So since it passed criteria 2, I now have to look at criteria 1. This one, however, if we look at it, does it decrease?
Yeah, right off the bat.
How do you know it decreases?
Because there's a bigger factor on the denominator.
That doesn't mean it's always decreasing. So let's look at it. If I plug in 1 to this, I get 1 over 2, right? If I plug in 2, I get 4 over 9, which I guess that's decreasing. If I plug in 3, I think this one actually is the cube root of 3 or 2, so it actually does there. So I guess you could say this one's decreasing without actually having to do much work. I'm gonna do some work with it just because I want to actually show you how to automatically test it. But yeah, this one, you probably wouldn't have to do that. What's the one way that we can always test to see if something decreases? What's the calculus way that we can determine the direction of a function, the slope of a function?
First derivative.
It's the derivatives. So we can take the derivative of this. So my derivative of this, it is a quotient. There you go, quotient rule. So hold on a second, lost my pen. All right, so quotient rule for this one. So it's the derivative of the top. So we've got 2n times the bottom minus the derivative of the bottom times the top. All over the bottom squared. So oh, I should have changed all those to x's. X. And this has got to be less than 0. So the numerator is the only thing that matters because the denominator can never be negative. So if I do 2x to the fourth plus 2x minus 3x to the fourth, we can simplify that down to 2x minus x to the fourth. Factor out the x, and the 2x minus 2x to the third. That has to be less than 0. So x is less than 0, or x is greater than the cube root of 2. So the reason this one works is because that's really just bigger than 1. That's why we were able to actually look at just the series. So we know this is going to be increasing or decreasing anything after the first term. So it passes criteria 2.
Wait, Professor. So 2x squared plus 2x minus 3x4, then you have equals
Yeah.
2x minus x to the fourth. I don't know how you got from there for that.
I just put the 2x to the fourth and the 3x to the fourth together.
Oh God. Okay. Nice.
The good news is we're almost done with class.
So then you went ahead and
Factored
just
it out. I pulled out
factored
the
it.
x. Because remember, when you factor it, it's easier to solve, set each one equal to 0 to figure out which one's going to be less than. So that's why I got the x is less than 0 to make it negative, or the second one's got to be greater than this cube root of 2.
Sorry, that's where I'm still getting a little confused. So what are we? So we're getting the test. So we're getting the But we already got the derivative. So what are we doing at this point? Trying to just simplify the numerator.
I want to find out when it's greater, less than 0. I want to find out when the numerator is going to be negative. So those are that's where it switches values, right? So in this situation, this value right here is going to be negative when x is less than 0. In this situation, x is going to be greater than the cubed root of 2 to make that 0 or to make it negative. So since my n can never be this, that doesn't work because my values always have to be positive and counting up by positive numbers. The only one that matters is that one. So I know it's going to be negative or decreasing when my n, or my series, my n is going to be greater than the cube root of 2, which is just greater than 1.
So why do you, the x might is less than 0? So we're saying
My slope is
Obviously,
my slope is negative. That's the goal. This is telling me when my derivative is negative, because that's when my slope is negative. So that's where my function is decreasing, which is what series. That's what sequence or the first criteria says, is that my series is my sequence is decreasing.
got it. Okay, thank you.
No problem. All right, we got one more. I saved the crazy one for last. Well, actually, I saved the simple one for last, but on purpose. All right, harmonic series. Harmonic series is 1 over n. That always what? A harmonic series, does it increase or does it does it converge or diverge? What did we say? One over n, that always diverges. That's the harmonic series, that always diverges. The alternating harmonic series, let's see if that converges or diverges. So if we look at that, so this series right here, it is most definitely alternating because it's got the -1 and +1 thing going on there. So it's going to keep switching back and forth. So we have to test our 2 criteria. So if I do the limit, as n goes to infinity of 1 over n, that does equal 0. So it passes criteria 2. Criteria 1 says b to the n plus 1 has to be less than or equal to b to the n. So I have 1 over n plus 1 is less than 1 over n. And that is also true. So while the harmonic series diverges, the alternating harmonic series converges. So the harmonic series diverges, but the alternating harmonic series converges. Yes, it's crazy like that. And that's going to come into play next class.